Welcome back to the lectures on chemistry, and in this series on the introduction to molecular spectroscopy, I would like to put some problems, sample problems, and also the method of solving them. Therefore, this is a video tutorial, and I hope it helps you to solve the regular tutorial problems of the course as well as towards the assessment in the final exam. These are elementary problems, and what I have in this is about 10 sample exercises, and I shall indicate the method of solution, not necessarily the final answer. I think that you can calculate, but you have to relate the problem to the concept that was presented in the video. So there is a question of, there's a collection of 10 problems here. And I also want to point out to the readers a very nice site that I came across by Professor Kit Peterson of the State University of Washington State University, yes. And the site contains a large number of physical chemistry course problems which are useful to you. So have a look at them. Now let me read the first problem and then indicate to you what is the solution. The first problem asks you to find the wave number, the frequency and wavelength of electromagnetic radiation consisting of photons, each with an energy of 2 electron volts. Okay. So this is a very straightforward relation that you have to remember, namely the energy of the photon is related to its wave number by the Planck's constant and the speed of light times nu bar. The second one is the energy related to the frequency in terms of the Planck's constant and the frequency, and the third is the energy related to the wavelength in an inverse fashion with the Planck's constant and the speed of light and the wavelength dividing it. Therefore, you are asked to calculate nu bar, you are asked to calculate nu, and you are also asked to calculate lambda for a given energy. Units are important. Important, please underline this. The unit given to you is 2 electron volt for the energy, and remember Planck's constant H is in the unit of joule second, 6.626 times 10 raised to minus 34 joule second. These are all SI units, and the frequency nu is in hertz or per second, and the wave number is in the unit of meter inverse. Since they are all SI units, the electron volt should obviously be converted to joules. You recall that 1 electron volt is 1.602 times 10 to the minus 19 joules. So if you remember that, then everything else is known to you. H is given, C is given, therefore nu bar can be calculated. H is given, H is the Planck's constant, so it's easy to write. It's already written down here as 6.626 into 10 raised to minus 34, and the speed of light, if you want to write, that is, for this calculation you can use the approximate value 3 into 10 to the 8 meters per second. So everything is given, therefore you only need to calculate the quantity nu. So the units are, I will write one step for cancellation for Hc nu bar as 6.626 times 10 to the minus 34 joule second. Please write the units always in every such problem, and C is given as 3 into 10 to the 8 meters per second, and you are asked to calculate nu bar, and the value given here is 1. This is 2 eV or 1 eV. This is 2 eV. Therefore, the energy given is 2 times 1.602 into 10 to the minus 19 joules per eV. Please remember, when you write the units carefully, these things cancel out in the correct manner. So, if you write this as 2 eV and you write this as 1.602 times 10 to the minus 19 joules per eV, you see the electron volts cancel. So, what you get is 3.204 times 10 to the minus 19 joules, and that is equal to 6.626 times 10 to the minus 34 joules second multiplied by 3 times 10 to the 8 meters per second. The second cancels off and these are equated, and therefore, you see that nu bar is going to be in terms of meter inverse, namely it is this is 3.204 into 10 raised to minus 19 divided by 6.626 into 3 into 10 to the minus 26, and the whole unit is 1 by meter. Okay. So, dimensions and units are extremely important, and therefore, in the similar manner you can calculate nu, you can calculate Hc by lambda. Okay. Let us look at problem 2. Okay. In the second problem, what is given are 3 energy levels in the order A less than B less than C, meaning the energy state A is like this, B is like this, and C is like this, and this is the increasing order of increasing energy. So, this is, you call it as A, B, C. The energy difference between A and C is 1 electron volt. This delta E is given, okay, and that delta E is 1 electron volt. And the wavelength of light required for resonant transition from A to B is 900 nanometers. This lambda is given, let me write it as delta E1 and write this as delta E2. Then energy conservation tells you that delta E should be equal to delta E1 plus delta E2, and you are given the wavelength for this transition as 900 nanometers. And you are asked to calculate what the wavelength of light required for resonance transition from B to C, that is this transition. Remember that delta E is inversely proportional to the wavelength, therefore, this is delta E and this one is delta E1 is given as 900 nanometers. Therefore, if you write Hc by lambda 1 plus Hc by lambda 2, and this is given as 1 electron volt, therefore, what you have is 1.602 times 10 to the minus 19 joules on this side, and that is equal to Hc times 1 by 900 nanometers plus 1 by lambda 2. Okay. Nanometers, therefore, recall the units carefully. You have 1.602 times 10 to the minus 19 joules, and this is given as the sum of two energies, 6.626 times 10 to the minus 34 times 3 times 10 to the 8. This is joule second and this is meters per second, and the joule and joule will go away, the second and second will go away, and what you have is 1 by 900 nanometers, which is 900 into 10 to the minus 9 meter plus 1 by lambda 2. Okay. So, once you take care of the units properly, you see how everything cancels out correctly, and you can see that lambda 2 will be given in terms of meters. Okay. This is something easy to calculate, please do that, complete the numerical exercise. Third problem. These are all very elementary problems. The purpose of discussing these problems in greater detail is to tell you the methodology of solving them, and also algebraically how you have to pay attention to details even if they are trivial, because at the end of it the devil is in the details. Please understand that. Therefore, the solution of any problem you have to pay attention to all the details. So, here the third problem tells you The usual frequency range for vibrational spectroscopy is 400 to 4000 centimeter inverse. Okay? This is in wave numbers. And you are given a typical vibrational stretching line at 2000 centimeter inverse, and you are all asked to calculate the energy corresponding to this 2000 centimeter inverse in two units, one as a joule per molecule and the other is as a joule per mole. A typical vibration refers to the change in energy in a single molecule. 2000 centimeter inverse means the energy required to raise the energy level of a single molecule. Therefore, this nu bar, which corresponds to a transition between, say, some vibrational state due to the stretching line having a V1 and a V1 plus 1. This corresponds to about 2000 centimeter inverse. This is centimeter inverse. SI units are meter inverse. Therefore, first of all, you need to make sure that nu bar is expressed in the right unit, namely, since it is 2000 by centimeter, it is essentially 2000 into 100 centimeter per meter, so that there is also centimeter here, that cancels off. Okay. So, what you have is 2 into 10 raised to 5 meter inverse. So, this is the nu bar given to you, and you are asked to calculate the J, joules per molecule, and that is given as Hc nu bar if everything else is expressed in the appropriate SI units. Therefore, you do the same thing, 6.626 times 10 to the minus 34 joule second times 3 into 10 to the 8 meters per second into 2 times 10 to the 5 per meter. So, you see that goes off with the meter, the second goes off with that, and what is left over is joules, and this is per molecule. And what is the value for per mole? Whatever that you get energy in joules per molecule, since there are Avogadro number of molecules in 1 mole, namely 6.022 times 10 to the 23 per mole, you can calculate the energy that you have done earlier, this number. You multiply this number by the Avogadro number, then you get the energy per mole. Delta E joules per molecule into 6.022 times 10 to the 23 molecules per mole. So, you have that, gives you joules per mole. Okay. So, dimensionally use these things, look at these things carefully. The next problem talks about the relative populations of molecules in a 2-level system. This is a model. The level 1 is called excited state and the level 0 is called the ground state, and the N1 corresponds to the number of molecules in the excited state, and the number N0 corresponds to the number of molecules in the ground state. Therefore, you are asked to calculate the population ratio subject to transitions that would occur due to electromagnetic radiation of 3 different types. Therefore, what you have in this problem is 3 different sets of energies, 2-level system. This is one system, E0, E1 with N0, N1. This is system 1 corresponding to a transition of 500 angstroms. The transition energy requires a wavelength of 500 angstroms. This is another system. I am not worried about the scale, but I am simply writing this as system 2 corresponding to a transition of 30 centimeter inverse. This is system 3, except that here frequency is given as 10 to the 17 hertz. Again, the temperature you will find out is an irrelevant data for this problem. You are given 3 different units for the energies and you are asked to calculate N1 by N0. Please remember the Boltzmann population formula for thermal equilibrium if the 2 energy levels are thermally at equilibrium with each other with molecules going up and down due to the absorption of energy and so on, then it's immediately you should remember that the number of molecules which are in any particular energy state E is proportional to this ratio, this factor exponential minus E by kBT. If the energy level is non-degenerate, that is it's only one function, one state for one energy, this is the formula, and therefore if you are looking at the number in the energy state E1 versus the number in the energy state E0, then you have to write this as, since the proportionality constant is the same for both of them, the ratio is exponential minus E1 by kBT with exponential minus E0 by kBT, where kB is the Boltzmann constant. It's a fundamental constant, and T is the temperature in Kelvin. In Kelvin. Okay. Therefore, the answer is exponential minus E1 by E1 minus E0 by kBT. Okay. If you go back to the problem, you see one data point is missing. Here T is equal to 27 is important. We need that data, T is equal to 27 or it's 300 Kelvin. Okay. So what you have is kB is known, kB is 1.38 times 10 to the minus 23 joules per Kelvin. Therefore, kBT means that T should be in Kelvin, so 27 degrees essentially means 273 plus 27 Kelvin, which is 300 Kelvin. So kB is known, T is known, and delta E is given by the corresponding either the lambda or the nu bar or the nu. Please remember, for this the delta E is Hc by lambda, and for this the delta E is Hc nu bar, and for this the delta E is H nu. So there are 3 different units used, and therefore in each one of them you can calculate. The only thing you have to remember is this is angstrom, and angstrom refers to 10 raised to, so if it is 500 angstrom, what it means is that 500 angstrom is 500 into 10 to the minus 8 centimeters, or it's 500 into 10 to the minus 10 meters. You have to use SI units and therefore convert everything into meters, seconds and joules. If energy is given in electron volts, convert that into joules. If the energy is given in calories, convert that into joules, and then it's easy to use the SI unit and calculate the ratio exponential minus E1 by E0, E1 minus E0 is that delta E corresponding to this number. So the lambda is 500 here multiplied by 10 to the minus 10 to give you the corresponding unit in meters, and this is 30 centimeter inverse, therefore you must multiply by 100 to give you meter inverse, and this is in the right unit hertz, therefore you multiply by H. So you can calculate delta E for this, delta E for this and delta E for this. There are 3 different models, 3 different what are called the pairs of energy levels, therefore you get 3 answers. The next problem, this is something I had also mentioned in my lecture. Show that for a diatomic molecule with 2 atoms of mass M1 and M2, the moment of inertia I for an axis passing through the center mass of the molecule and perpendicular to the bond axis is given by the formula I is equal to mu r square. Okay. Now, what is the picture? The picture is you have a diatomic molecule with two different masses m1 and m2. The center mass is closer to the heavier nucleus, and you are asked to calculate the moment of inertia about an axis which is perpendicular to the bond axis. This is the bond axis, and this is the center mass point, the origin, okay, for this system, the center of mass. Okay. And if you know that the radius vector of this atom from this origin is r1 and the radius vector of the center of this atom from the origin is r2, then the interatomic distance r, let me write with the proper vector unit, the interatomic distance r is, given that one direction is positive, suppose this is the positive x axis, then r2 is positive but r1 is on the opposite side, therefore r will be r2 minus r1 vectorially. And what is the moment of inertia? The moment of inertia is m1 r1 square plus m2 r2 square, because r1 and r2 are the perpendicular distances of the two masses m1 and m2 from the axis about which we want to calculate the center of mass. So, m1 r1 square and m2 r2 square. This is what is to be rewritten as mu r square, where mu is the reduced mass m1 m2 by m1 plus m2. Okay. And the radius vector, the distance vector r is related to the two vectors r2 and r1 by this choice, but also please remember the definition of the center of mass means the following, that m1 vector r1 plus m2 vector r2, that should be 0, because the center of mass is also the origin. Therefore, if it is a pure vibration without the molecule moving anywhere, then the pure vibration essentially means that the center of mass remains where it is. That means this condition is satisfied for any vibrational amplitude r. Therefore, m1 r1 plus m2 r2 is 0, and vectorially, and the internuclear distance vector r is the difference r2 minus r1 because of the choice of the directions. With this, you have to do a simple substitution and get the answer. Let me write that down. Okay. So, what you do is, given the fact that r is r2 minus r1, I think that is what I had written, I understand, r2 minus r1, yes. Let us write r2 is equal to r plus r1. The condition that m1 r1 plus m2 r2 is equal to 0 gives you also r2 is equal to minus m1 r1 by m2. If you substitute that, you get the result, namely r2 is this value, r plus r1 is that. Therefore, from these two you can get the expression r is equal to minus m1 r1 by m2 minus r1. Okay. r2 minus r1, therefore, that is what you have. So, this is the definition of r using one vector r1. Now, I is m1 r1 square plus m2 r2 square. So, let us replace r2 by whatever we have, namely m1 r1 square plus m2 times r2 square, which is m1 square by m2 square times r1 square. These are scalars, therefore, the minus sign goes away, And so what is left over is you have m1, if you take the common factor, m1 m2 square r1 square plus m2 m1 square r1 square divided by m2 square. Okay. So, this you have to substitute, the r1 you have to substitute into this. If you do this substitution of r1 as given here using r, okay, what is r1? R is minus m1 plus m2 by m2 times r1 from this equation. Therefore, r1 is m2 r with a minus sign divided by m1 plus m2. Okay. So, if you substitute r1 square here, you will get immediately the expression that I is equal to m1 m2 by m1 plus m2 times r square. Okay. Please remember, this is nothing other than m1 plus m2 by m2 times r1 square. So, substitute this and you get the moment of inertia I as this value. Okay. This is a standard expression, it is a very simple algebra, but that the vector notation has to be taken into account and you must know what is meant by the center mass. Okay. This is used in rotational spectroscopy in diatomic molecular systems. Now, the next problem, in this problem we are asked to calculate the force constant in the unit of Newton per meter for the hydrogen bromide molecule, given that the fundamental frequency is given as for HBr it is 2650 centimeter inverse, and also calculate the same for carbon monoxide, that is the force constant, given that the frequency is given as 2170 centimeter inverse. And you are also asked to calculate on the strength of the bonds based on your result. Okay. First of all, remember from the elementary vibrational spectroscopy that the fundamental frequency nu in hertz is given as 1 by 2 pi square root of k by mu. Mu is the reduced mass of the diatomic mass. K is the force constant. Remember the unit Newton, that is basically kilogram meter per second square. Force into distance is energy. So, given that Newton meter inverse is kilogram per second square, that is the force constant K, the unit. Okay. The reduced mass mu should be in kilograms, therefore, nu will be square root of second to the minus 2, and so it is hertz. Okay. So, this is hertz. You are given nu bar as 2650 centimeter inverse. Therefore, what is the relation between nu and nu bar? Please remember this is hertz, and I think you will remember this as per meter, and it is meter per second, which is the speed of light, gives you per second. So, the relation is nu hertz is C nu bar, and nu bar is in centimeter inverse. Since you are using SI units, convert that as C nu bar into 100, you will get the hertz. Okay. So, these are the things you have to remember. What about the reduced mass? For HBr, if you use the atomic masses simply as 1 and 80, I am not worried about the details, you can actually put the exact number, but the process is 1 and 80, then the reduced mass is 80 into 1 divided by 81, M1 plus M2, and this has to be divided by 6.022 into 10 raised to 23 to get the mass of one molecule in grams. Therefore, you have to multiply this by 10 raised to minus 3, 81 into 6.022 times 10 to the 23. So, that would give you kilograms. Okay. So, given then nu is equal to 2 pi nu is equal to square root of k by mu, you get immediately k is equal to 4 pi square C nu bar, because that is nu, times mu. C is known, nu bar is known in meter inverse, mu is known, therefore you calculate k. K you calculate for HBr, K you calculate for CO using the reduced mass for CO, this expression, namely 12 carbon 16, 12 into 16 divided by 28 into 6.022 times 10 to the 23 and also multiplied by 10 to the minus 3 to give you the kilograms. Therefore, for carbon monoxide you know the mu, for carbon monoxide you are given the nu bar in centimeter inverse, convert that into meter inverse, put the C in meters per second, and then you see that you can calculate K. Find out which is greater than which. The larger the force constant, the stronger the bond. Larger the K, the stronger the bond. Therefore, you can find out which of the K, the carbon monoxide or HBr, is larger, and you will see this. All the numerical results, the numbers will be there in your website along with the problems, but this is how I would like to pay attention to the details. Now, the next problem is something very similar. For hydrogen chloride, calculate the maximum amplitude of the lowest vibrational level. Can the molecule be approximated as a simple harmonic oscillator? And what are given? You are given the force constant, and since the molecule is given as HCl, you also know that the reduced mass can be calculated. What is meant by the maximum amplitude of the lowest vibrational level? What it means is that if the entire energy of the harmonic oscillator is vibrational potential energy and it is equal to half kx maximum square. Please remember, if you do a classical model, if this is the energy, these are called the turning points in the classical model corresponding to the maximum amplitude of vibration, where the potential energy is equal to the total energy. Right in the middle, that is at the equilibrium position, the molecule has no potential energy because we assume that the potential energy is 0 at equilibrium distance. Therefore, the entire energy is kinetic energy, therefore the molecule has the maximum vibrational velocity. So, you have two conditions, that at the turning points half k x maximum square, sorry, this is x maximum square, x maximum square, that is equal to E, and in the middle half m V max square is equal to E. So, if you are asked to calculate maximum vibrational amplitude, that it means essentially the potential energy is all the total energy, and since you are given the value of k and you are given the value of E, you can calculate x max square. Pay attention to the units. If in a similar problem, if somebody asks you what is the maximum vibrational velocity, what it means is that assuming that the molecule has no potential energy during that vibration, meaning it is right at the equilibrium during the vibration, what is the speed of the atom? This is a classical model. So, either way you can calculate. K is given as kilogram per second square. Therefore, you can calculate E, the equilibrium bond length is given, and in order to calculate E, you also need the vibrational energy in the ground state. Therefore, you need as an input vibrational energy in the ground state. That can be calculated as, remember, the frequency nu is 1 by 2 pi square root of k by mu. Since k is given and mu can be calculated for HCl, you know what the nu is. And once nu is known in hertz, the energy E is h nu. Okay? Therefore, the energy is known. And immediately you can write that this energy is all half k x maximum square, giving you x maximum is 2 E by k square root, and if k is if k is known, E has been calculated, therefore x max can be calculated. Okay. Now, why are we given the data? Equilibrium bond distance. Equilibrium bond distance is 127.4 picometers. This is our equilibrium is 127.4 picometers, meaning it is 127.4 into 10 raised to minus 12 meters. Okay. If you calculate x max, and if the x max is very large compared to the equilibrium bond distance, then what it means is that the molecule at that lower energy level, its vibrational velocity is such that the harmonic model is meaningful. If, however, the maximum bond length is very far away from the equilibrium, then you have to think about it. Okay? Whether the vibrational, the enharmonicity, the harmonic model is appropriate to that of the equilibrium bond distance. Therefore, at this energy, if the maximum amplitude is very close to the bond distance, then what it means is that the vibrational amplitude is not very different from, is very small, and therefore the equilibrium bond distance and the fully stretched vibrational molecule, the two bonds are very close to each other. For example, if this is that, or E given by 127.4, and corresponding to this energy, this number is a fraction of 127.4. If it is less than, say, 10% or 5% of 127.4, then it makes sense that the vibration is harmonic because the amplitude of vibration is very small. If it is a very large number, then the amplitude is very large. If the amplitude is very large, then the harmonic model breaks down. Therefore, when you calculate x max, you will know how close it is to the equilibrium bond distance, and that will give you the picture whether the molecular vibration at that energy is nearly harmonic or not. Okay. So, you look at the numbers given in the website for as solutions. The next problem talks about the vibrational frequency dependence on the masses of the reduced masses of the atoms, and here the OH stretching vibration corresponding to the reduced mass species OH is about 3600 centimeters. So, if you write to the nu as 1 by 2 pi times k by mu, this mu corresponds to mu of OH. Assuming that the force constant of the bond to remain the same due to isotopic substitution of H by D. So, let us call this as nu 1 corresponding to OH. We are asked to find out the expected shift in the stretching frequency. So, if this is nu 1, it is 1 by 2 pi k1 by mu OH. You are told that the force constant is the same. Therefore, if there is any difference in the vibrational stretching frequency, it is due to the fact that it is k1 by mu OD. The reduced mass of OD and OH are different. Please remember, OH is 16 into 1 by 17 times 6.022 times 10 to the 26, if you want to write this in kilograms. Okay. Whereas the mu of OD, if you remember, is 16 into 2 by 18, 16 plus 2 times 6.022 into 10 to the 26 kilogram. Therefore, the mu of OD and the mu of OH are quite different, and since it is an isotopic substitution, if the force constant remains the same, the bond strength is very much the same, then what is a shift in nu 1 due to the substitution? Therefore, you are only calculating the ratio nu 1 by nu 2 as 1 by 2 pi square root of k by mu OH divided by 1 by 2 pi square root of k by mu OD, and obviously after cancelling, what you see is mu OD by mu OH. So, you can see the ratio nu 1 and nu 2, and therefore, if nu 2 is substantially different from nu 1, you can see that this number OD is bigger than the number mu OH, and therefore, the nu 1 for OH is more than that for nu 2. The vibrational frequency is reduced when you substitute with a heavier mass, and because it is inversely proportional to the reduced mass, and you can see immediately that nu 2 will be different. What is the difference between nu 1 minus nu 2? That is the shift in the vibrational frequency, is the shift. So, substitute the numbers here and you will immediately get the answer. Okay. The next problem is on the Beer-Lambert law. A certain solution in a cell absorbs 10% of incident light. What fraction of the incident light will be absorbed in a cell 5 times longer? I think I changed that number from 10 to 80%, just to get some logarithmic ratios reasonable. Okay, 80% of incident light. So, recall the Beer-Lambert law that the absorbance, which is the logarithm of incident intensity of light to the intensity of light that is emitted, that is the molar extinction coefficient epsilon times concentration of the substance times the length of the cell. Now, when you say a cell absorbs 80% of incident light, what it means is that obviously when I naught and I are looked at, I is 20% of I naught, because the rest is absorbed. So, when 80% is absorbed, what it means is 20% is transmitted. Therefore, I naught by I is 5. So, you know log 5 is some epsilon for that substance times its concentration times the length of the cell. Now, you are asked to calculate what is the corresponding log I naught prime by I prime, if the concentration of the cell remains the same, concentration of the substance remains the same, but the length becomes 5 times the length of the cell, a cell 5 times longer. So, you can calculate this number by taking the ratio, because this goes away, this in the ratio when you divide, the length also goes away. So, what you have is log 5 by A prime due to the 5 times longer length is 1 by 5. Therefore, you can calculate A prime as 5 times log 5. Log 5 is 0.6990, so you have 5 times 0.6990. That is A prime. But what is A prime? A prime is log I naught by I. Therefore, from this, taking the anti-logarithm of this value, you can calculate I naught and the ratio I naught by I. So, if the ratio, for example, is 3%, if what it means is that the ratio is not 3%, if the ratio is 33.3, what it means is that 3% of I naught gets transmitted, the remaining 97% gets absorbed. Therefore, based on the anti-logarithm, you can calculate I naught by I as anti-log A prime, and from this you can get the value of I as the fraction sum of I naught. Okay. So, this number will also be there in the text. The last problem is again on Beer-Lambert's law, and it talks about another compound, methanol, absorbing at a particular frequency, particular light wavelength, and it has an absorbance of 150 dm cube per mole per centimeter. So, absorbance is A given by epsilon concentration into length L. Epsilon is given as 150 dm cube per mole, and the concentration of the cell is given as 0.01 mole per dm cube, and the length of the cell, this is C, and the length of the cell is 1 centimeter. That is also here per centimeter. So, dimensionally absorbance has no dimensions, okay, so that cancels that, and the dm cube mole inverse is the inverse of the mole dm cube. So, what you have is 1.5, okay, absorbance is 1.5, and what is the percentage of light transmitted? This is equal to log I naught by I. And in this case, if I have looked at the numbers, I think it is about 31 point, that is I naught by I is a log of 1.5, it is about 31.7. So, what it means is that I is 31.7 times less than I naught. So, the percentage of light that comes out is roughly 3.15%. Because if that is what it is, I naught by 31.7 will be I, and that is 3.15%, okay, of the original I naught. So, these are simple ways of manipulating elementary exercises. Of course, you have to learn more and more about the computations of small parameters as well as the numerical parameters that you need to calculate in solving these problems. And let me share with you the last slide of the PPT, which contains these problems in text form for you. Let me go to the presentation. The last slide is quite important. Most important, whatever you do, you have to enjoy your learning, and if there are problems of similar nature that you want to solve in this course by looking at textbooks and other sites, please do send and share them with the other students in the website. But please remember, even though I have given you a tutorial, please remember, learning is only reinforced through these problem solving methods. It's not the other way around. You don't learn by solving problems. Your learning is through understanding a concept, thinking about it and discussing that. Problems ensure that the way you have understood that concept is reinforced by solving them right. Therefore, please remember, learning is only reinforced through problem solving. It is important, but problem solving is a necessary, it's not a sufficient exercise to understand a subject. Therefore, please read more, please listen to the lectures, please find your own problems, and online learning through this course or by any other course on your own is actually by self-motivation. And while I continue to solve similar problems, I wish you all the best. Thank you.